Hey, thanks for having me. I'm super happy to be here. So my name is Matt Layher. I work as an engineer at Fastly. So thanks for having me today. I'm going to go through this pretty quickly because there's a lot of kind of network stuff to cover. Feel free to interrupt me and ask questions. I definitely like that during a meetup. It's a little more casual that way. Also, I will be giving a talk at GoCon Canada, so I'm super excited. Would love to meet you all in person there. And without further ado, I will go ahead and share my screen. Okay, so we should have the slide deck up right now. So yep, I'm Matt, I work at Fastly. Today's talk is not about Fastly, it's all about my open source work, but we're gonna have some fun talking about Ethernet frames. So I originally presented this talk in 2017 at GopherCon as a lightning talk, but a lot has changed since then, actually. So let's start from the very beginning, kind of the basics of what Ethernet frames are and why you should care. So as far as our problem statement goes, Go's package net only provides IP, TCP, and UDP connectivity. But what if these protocols are too high level for our use case? Or what if you'd like to implement something like ARP, DHCP, ATA over Ethernet, LLDP, many other things? Or what if you need absolute full control over your application's traffic? So one possible solution to this problem is to send and receive Ethernet frames directly in Go. So very, very low level on the wire, just above essentially the electrical signals. And you can actually do this using two packages I've created here, Ethernet and RAW. And RAW implements a RAW and/or packet socket used for sending Ethernet frames. So what is an Ethernet frame anyway? An Ethernet, aka Ethernet 2 in this case, frame, is the fundamental unit of layer 2 data transmission. So it's got a few different fields here. You've got the destination and source MAC address, which is the hardware address of your network interface. You've got the ether type that specifies the type of traffic this is carrying, such as IPv4, IPv6, ARP, and etc. You've got an arbitrary payload, which is typically going to be like your IP headers. And you have a CRC checksum. This verifies that the frame was not corrupted on the wire. So let's say, for example, we want to create an Ethernet frame in Go. We're going to create a frame that can be sent as a broadcast message. We use the Ethernet package and create this frame structure. So we have a destination set to Ethernet broadcast, which is actually all Fs in the MAC address. And this means that every device on your network that sees this will broadcast it. So your switches will send it out of every port, and every machine on the same network segment will be able to see this. We're going to identify our machine as the sender, some random MAC address. We're going to pick an unused ether type. Lots of ether types are reserved for things like IPv4, IPv6, etc. So we're going to pick a totally random one, all C's in hex. And let's send a simple message that says, hello world. So once we have our frame actually crafted, we want to marshal it to its binary format so it can actually be sent over the wire. So we invoke the marshal binary method. This is going to store everything, and now it's suitable for sending over a network interface. One thing to note here, the kernel will typically take care of the frame check sequence for you, but if you were doing something like a tap interface in user space, you would actually call the marshal FCS method instead, and this will give you the frame check sequence. So while we're here, I'm also going to talk about VLAN tags. So a VLAN tag is kind of like a clever extension of an Ethernet frame that lets you divide one physical network into many logical segments. So there's a special ether type that indicates when a VLAN tag is present, and once you see that, the parser is able to know that there are 2 additional bytes in the frame that indicate the VLAN information. For the purposes of our talk today, all we really care about is the VLAN ID or VID. There are up to 4096 different VLANs, so you can take one physical network and split it into 4096 logical ones, which is pretty cool. So let's say, for example, we want to do our same frame, but we only want machines that are running on VLAN 10 to actually see this. The fields are exactly the same, but we can also specify a VLAN field with this VLAN structure and specify an ID of 10. So at this point, we want to actually send this over a network interface. In order to actually do this, you have to leverage some operating system specific APIs. So on Linux, this would be BSD sockets using the AF packet family. On macOS and the other BSDs, there's what's called a BDF device that can do this. On Windows, I'm actually not sure, but I'm pretty sure something like libpcap or similar will be able to do this just fine. The basic idea is you open a handle to your network interface, you pass it to this raw listen packet constructor here, specify the ether type you actually care about for your traffic, and from here, it's just a regular net packet con, and you can treat it as such in your application. So let's say, for example, we have the same Ethernet frame bytes we had before with our hello world message. We create this address that specifies the destination address of the frame. This is kind of funny because like in Ethernet, the destination address is actually carried in the frame as well, but I believe at least on Linux, you have to specify this too. On BSD, I don't think it matters. We call write to, and we're actually writing our raw Ethernet frame to the network using our net packet con implementation. From here, we can also read incoming frames. So we're going to look for a byte slice that's up to our MTU maximum transmission unit of our interface in size, read individual frames, and then we can unmarshal them into an Ethernet frame. Somebody asking a question?
Nope.
Nope, okay, moving on. So today, I've actually made quite a few improvements to package raw over the last time I gave this talk. So now, we have timeouts that are fully implemented on Linux, at least, using the Go112 runtime network polar support. So I'll dig into this in a little bit, but basically we can leverage the runtime in a very efficient way to take care of things like timeouts and asynchronous I/O for us, which is extremely cool. So this type fully implements the net packet-con interface, but it's still a bit rough around the edges. So for example, I'm not actually returning net op error implementations, I'm returning raw system call errors, which is not super great, so I'd like to work on that. At one point, I was considering trying to move this to golang.org/xnet, and there was consideration for doing so, but these days it sounds like more and more libraries are trying to be moved out of the X packages. This is going to remain on my personal GitHub for some time. So with that all being said, let's do a couple of demos here. So first, I'm going to show a command called ether echo. It's a super basic kind of hello world for this package. It can broadcast a message to all machines on your same network segment. And next, I'm going to look at some of the internals of raw. We're going to look at the Linux implementation in particular under the hood and see kind of how the system calls and the polar integration fit together. So as far as raw goes, sorry, what was that? Oh, sorry, I think I'm hearing my own echo. Anyway, so as far as raw goes, we have a pretty basic API. It implements the net adder and net packet con types. So we have our net adder implementation and our con, and the con type here actually has all the methods of net packet con, but also a couple additional ones that are useful for working with Ethernet frames. We have set BPF, which can actually attach a BPF filter to filter packets in the kernel, pretty cool. And also set promiscuous, so you can actually receive Ethernet frames that are not necessarily bound for your machine, which is a pretty interesting thing. So let's look at how ether echo is actually implemented. So we're going to take that ether type we used before, this all C's, and use that for our fake traffic here. We open handle to some network interface we specify with a flag, typically primary Ethernet interface. And then we're going to call raw listen packet. This will actually create our net packet con type. It will listen for traffic on this interface with our specified ether type. As far as a message to send, by default, we're going to send the host names of the machines, and we're going to start a couple of Go routines here to actually send and receive messages. So when we're sending a message, we're going to assemble an Ethernet frame and broadcast it to every machine on our same network segment. We're going to say it's from our machine with our specified ether type, and whatever payload we specify, in this case, something like hello world or the host name. We marshal it to the binary format, and then from here, we're going to start a ticker and just keep sending this over and over and over again. And this is going to continuously send these frames and broadcast it to every machine on your network segment every second. As far as the receiving end, we create our Ethernet frame, and then we're going to read bytes off of the network interface directly into this buffer. Once we actually have the bytes, we unmarshal them from the binary format into the Go representation. And from here, we're able to do things like look at the source and destination addresses, and etc., and also look at the payload, ether type, VLAN, other fields. So to see how this actually works, I've actually got this running on 3 separate machines, and I will start it up in a sec here. So the top is my desktop. The middle is actually my Ubiquiti Edge Router Lite. I've cross-compiled the binary from BIP64, which is pretty cool. So Ubiquiti stuff is just Linux underneath, which is awesome. And then for the third machine, I have my server. So if I start this on one machine, you're not really seeing anything happen. But if I start this on 2, we'll start to see these machines are actually talking to each other. So they're both broadcasting frames to every machine on the network. And when I start the third, as we can see, we're seeing the Ethernet frames actually being broadcast from all 3 separate machines. And any other machine on my network right now that was listening to this could also see this traffic as well. This is kind of a cool use case. Like, you can't actually send this traffic over the internet, but you could probably do some interesting things over your local area network. So now that we've covered that, I'd like to talk a little bit about how this is actually implemented under the hood with the system call stuff. So we have this con type, and this is actually going to be the cross-platform portion of the code. High-level interfaces, documentation, but then we have this internal packet con type that's actually going to implement the internal methods for things like the Linux implementation and BSD implementation. So we have our methods such as read from, write to, close, etc. But under the hood, things are a little bit more tricky. So the basic idea is that we're going to call this listen packet constructor, and this is where the operating system specific code begins. We call it Unix socket. This is actually going to open up an actual socket using a system call. So now we have a raw file descriptor that we can use to actually send and receive frames and such. So something pretty tricky we're going to do next is we're going to turn this socket into a non-blocking socket. So typically this would mean that if no data was available on the socket, you'd see something like a Unix E again error. So this is kind of like interesting because suddenly you have to deal with this different error type and make sure that the socket's actually ready. But as it turns out, the runtime network puller can actually do a lot of the work for us. If we take our socket file descriptor and put it in this OSU file function now, as of Go 1.11, I believe, this actually registers the file descriptor with the puller. And finally, as of Go 1.12, we can call this syscallcon method on this file. So this is an OS file wrapping our raw socket descriptor, and when we call syscallcon, we actually get an interface that can be used to perform raw reads, writes, and control methods on this thing. So from here, we'll talk about this important in a sec here. But from here, we're able to do things like bind to the interface, actually perform the rest of the BSD sockets kind of dance, and now we can actually send and receive Ethernet frames. So the way this is implemented is I have this read from method. Remember, this is the Linux specific code. It's going to invoke this receive from system call. So if I scroll down a ways here, there's a lot of stuff going on, but right. So if you remember that syscallcon we talked about earlier, syscallcon returns a syscall rawcon type. The rawcon has a method called read. It takes a function, and essentially you can think of it as this function is going to be executed by the Go routine within the runtime network puller. So we're calling Unix receive from, which is a system call directly on the file descriptor handed to us, and the file descriptor is being managed by the runtime network puller. If we see an error here that says that the socket has received an E again, meaning that the socket is not ready for reading, so there's no frames available, the runtime network puller will take note of that, put our Go routine to sleep, and it will actually be able to wake us up later on. So we don't actually have to do any kind of looping or polling or implementing things like select and epoll ourselves, because the runtime is actually using epoll, which is a Linux-specific API for polling sockets for readiness, under the hood to make this all work. So putting this all together, we now have an API that appears to be blocking, but the runtime is doing a lot of work behind the scenes to actually make this happen. The same ideas apply for write, except for calling Unix send to. And what's also extremely cool about this is that deadlines just work. So the OS file type has these set deadline methods. We're actually able to take all three of these and call them, and this will set a deadline within the runtime, so we can actually implement proper timeouts. Okay, so that was a lot, but now that we're all done with that, so if you're interested in more information on these kinds of topics, you can check out my Ethernet package and my raw package on GitHub. I've done a blog post that covers this in detail called Network Protocol Breakdown, Ethernet and Go. And if you're interested, you can also check out the prior version of this talk from GopherCon. Although a lot has changed, so maybe for historical purposes it's fun, but definitely check out this talk instead. So that's it. Thank you very much.
Okay, so I'm not sure that the mic on my laptop is great here, so if you want to ask a question, I'm going to try and repeat it so that Matt can hear here. Does anyone have any questions, or go for it?
What was your initial use case for this? What did you have?
So could you hear that at all, Matt, or?
Yeah, what was my initial use case for this?
Yeah. Okay. Good. Okay. Sweet.
Yeah, so I think kind of curiosity was really what it came down to. I think the first package I implemented with this was an ARP package. So essentially being able to send and receive like ARP over the network, determine the hardware address of devices using their IP address, which is what ARP does. And ARP is this weird old protocol that runs on top of Ethernet instead of on top of IP, like the IPv6 equivalent NDP. So I originally did it for ARP, but I've also found different use cases. Like I've implemented THCP with this, I've implemented ATA over Ethernet, LLD, a few other things. I think basically this is kind of a fun, different way of doing low-level networking in Linux with Go. And I think it's really interesting to kind of explore these operating specific facilities.
Cool.
Thank you.
What kind of performance would you get?
So I think somebody asked, what kind of performance could you get?
So it's worth noting this isn't actually like optimized for performance. I could probably do more interesting things like saving buffers and possibly some more advanced installs. But in my experience, this is enough. I actually, the CoreOS folks had a project called Taurus at one point that had my ATA over Ethernet implementation in it. And this is actually all backed by this. So you're literally sending Ethernet frames over the network to like operate a network storage device. So pretty interesting stuff. And as far as I can tell, it had decent performance. But that being said, it wasn't my explicit goal. But if I decided I needed to make that happen, I could probably do so.
Cool. Cool. Go for it.
Could you explain the benefit of the Go 1.12 runtime bring to the table?
So could you hear that, Matt? Or
Oh yeah, can I explain the benefit of the Go 112 runtime network polar integration?
exactly? Yeah.
Yeah, totally. So beforehand, basically your options were you could have all blocking sockets, so people can't set timeouts, people can't close the Go routine concurrently. So you're kind of violating the NetBack account interface. So it's not ideal. So that's if you're all blocking. If you set it to non-blocking, or you do things like setting socket options to set timeouts, again, you have to keep managing this internal state. There was one point where I was setting a timeout every 100 milliseconds. So it was essentially doing one top-level read, but then just reading over and over and over again, and kind of like spinning, but doing like a small sleep. Also not ideal. So as a third option, I could have set my sockets to non-blocking and done epoll myself using like Unix, epoll, waits, all this stuff. But you also end up with like a lot of complexity. And the runtime has a facility that already does this for you. The runtime's been able to do this with TCP, UDP, etc. sockets for ages. So what this comes down to is at Go 112, we can finally integrate and use all those facilities for our custom socket types instead of just recognizing TCP, UDP, IP.
Cool. Cool. Any other questions? No? Okay. Well, thanks so much, eh?
Yeah.